Hello, everyone. Thanks for joining. So today we are here to do a deep dive session on Hive. And we have our honorable speaker from Cloudera itself, Zscolt and Kokila. So Zscolt will start with his introduction and he will talk over the basics of Hive. Then Kokila will move forward, take the session forward and do some deep dive in that. So thanks everybody for joining. And over to you, Zscolt, please.
Thank you, Samriddhi. So first of all, let me share my screen because it is easier with screen share. Yep. Okay. So first of all, let me a little bit be more precise about the first session. I wouldn't say it is a deep dive. It is rather a high-level overview of Hive. And after that, Kokila will go a little bit deeper, or I would say much deeper with Compaction. And as far as I know, we will have two ongoing presentations at other meetups or meetup about other topics of Hive. So again, this will be a high-level overview of the Hive architecture and the very basics of it. Okay, let's start it. Yeah, a very quick introduction about me. Actually, I'm in the industry for a couple of years by now, and accidentally it happened in the way that I was always working with data some or other way, and that led me to Cloudera maybe 1.5 years ago. So I'm pretty new for big data, but I hope I can share you some basics of it. Okay. And before we go to Hive, let me tell a couple of things about the history of how we can store data. The most trivial version is a post-it. You know, we have something that we have to remember, we write it on a post-it and put that sticker to somewhere. It can contain a couple of lines. It depends on the size of your letters when you write. You know, the next logical and also computer supported version is a text file. It's basically a single file that you can write anything into that. It can contain a large amount of data, but in exchange, it is pretty hard to consume it. So you can imagine that you have a text file with 100,000 lines, and somebody wonders, okay, what is the value in the 20th 100 line? It will be hard to consume, especially if you are an average user. The next logical step is an Excel sheet. I know there are multiple software like Excel, but let's be honest, Excel is the de facto industry standard, and half of the businesses around the world works based on Excel. It has a huge benefits comparing to text files because it is pretty easy to consume the data. That means you can easily search for values and you can do basic data manipulation on that. So I would say it is an important step. But also it has its own limitations. Maybe if somebody old enough, they can remember that there were 65,000 rows limit on Excel sheets a long time before. It was because of the way how it stored data. Since that limitation has gone, but still I wouldn't even recommend to anybody to store millions of lines of data in Excel sheet. So from Excel, let's be honest, we have to move forward. And now we get to databases. But before we go to Hive, let's a little bit talk about relational database. It is a huge step forward. From that, we have some unified way to get the data from the database, and we can store a large amount of data. That is the point when we need an expert to store the data. That's the first major point. And unfortunately, that can be still too less. Sometimes we have data that is far beyond the limits of the relational database. We can imagine that how many data banks and car manufacturers can have. They can basically have data about any single person around the Earth's globe. So that is the reason why I want to introduce Hive. And because Hive is a data warehouse system, and Hive is something that actually allows you to scale the data in a way that is hard to imagine how many. So later a little bit, I will talk about the scale of that data. But this presentation about explaining what is Hive, how the Hive architecture looks like. To understand what is Hive, I think that sentence is the most important thing. It is in the start page of Apache Hive. And that says Apache Hive is a distributed, fault-tolerant data warehouse system that enables analytics at a massive scale. Hive Metastore provides a central repository of metadata, and so on. It's a very large definition, and it contains a lot of words that we cannot even understand at this point. So let's talk about them. The first is how many data we can store in Hive. I would say that it is pretty common to have petabytes of data. Okay, but what petabytes of data means? The average user doesn't even know what a gigabyte means, but as we are technical persons, I assume that we know what is a gigabyte of data. But for a fair comparison, I checked my computer that I'm working on. It has 500 gigabytes of storage capacity. The 500 gigabytes, that actually it's pretty far from the limits that we can call 1 petabyte. So as we can see, 1 petabyte is 1 million gigabyte. It is another, I would say, it is a so large difference that it doesn't even worth to compare. The easiest way to say that if we have more data than we can imagine the scale, then we are closing to something that we can call big data. And also the other common point about is that in that case, we have data that we cannot even store in one single computer, or not only on 10. Maybe we can store it in 1,000 computers or 5,000 computers. So that is the scale that we can imagine. So now, if we go back to the previous definition that we discussed what petabytes of data means, that means a very huge amount of data. To be able to understand Apache Hive, we have to talk a little bit about Apache Hadoop, because I usually call Hive and also Hadoop is a huge software created from Lego bricks, and those Lego bricks stick together, and we get some large software from them. And actually, both Hive and Hadoop is a collection of software, I would say. And Apache Hive is built on Hadoop ecosystem. Why? Because Hadoop said something that is pretty important from the Hive perspective. there is something in that slide that's called HDFS. It is a Hadoop distributed file system. That will be the base of our Hive architecture because, as I mentioned, we have petabytes of data, and we have to get, and we must have some place to store that amount of data. And actually that means that we have the whole Hadoop ecosystem, and part of that there is that HDF, something called HDFS, and that will be the software that manages the storage layer. I mean that we can relatively easily put 1,000 computers into that HDFS, and it will be act like as our single computer that we are currently staying at. And also, it as that slide shows, it also solves some important problem about storing data in that distributed ways, because that is thing that we call distributed. When we distribute our data around 1,000 computers. So there is two things. The first is replication. That means that we duplicate the data between those computers. We will call that nodes from that point. And that actually helps us to make sure that if we have any disaster, we can recover from that. So you can imagine that you have two computers, one of them goes wrong, so still the other can provide us the data. And also we can optimize reads because, you know, we have multiple nodes and the same data is replicated to those nodes, so that when we have a single read, there can be multiple computers that serves us. And also, as I mentioned, it acts like something like a virtual file system. So if you check that part of the slide, actually we have a similar file system structure on Hadoop as we have any kind of Unix-like file systems. And we call those computers data nodes. And as we can see again, the data is duplicated around the nodes. Okay, that actually solves the problem of distributed and also solves the problem of fault-tolerant, because that means, as I mentioned, that one of our nodes completely dies, other nodes can take part of its job. And also some interesting stuff about that, because we have actually two major ways to store data. We can buy a data center or multiple data centers and build those data centers with thousands of computers, or we can purchase it as a service from providers like AWS. The most common storage version is the S3, that is part of the AWS stuff. That basically means that it stores our data in a cloud. Okay. And yeah, as I mentioned, it is a Unix-like file system, and all of the major cloud providers supports it. Okay. Now let's move forward to our, sorry, I have no idea why my presentation jumps around. Let me check it, because it shouldn't jump around. Okay, the next thing that we want to check what it exactly means, it is what we call data warehouse, because as I mentioned, Hive is a data warehouse. Actually, if you want to narrow down, data warehouse is some software then can integrate our data from multiple data sources, so that we will have one common place to consume all of our data. And it is pretty common to use something called ETL. That means, we at the multiple data sources, our data is in multiple formats. So we have to unify those formats and put it into our data warehouse system, in our case, into Hive. And it is a pretty common ETL process, how we can do that. So now we know what the data warehouse system is. As we can see, our picture gets a little bit cleaner. But there is something else that we can call data lake. It is the other side of the coin. So as we can imagine, data warehouse is our system when we collected all the data and we gave it some structure. And the data lake is a huger, it's a larger scale of the whole. I would say that Hive is one of the possibilities that we can use in our data lake ecosystem, because the major difference between data warehouse and data lake from our perspective, that a data lake, we have no structured data. And actually we can build a whole ecosystem around that, and Cloudera does it as well. And in our enterprise data lake, we can have our data warehouse. And of course, Hive is our data warehouse. Okay, so Hive supports data lake architectures. Okay. Other important thing, we have thousands of computers and we have a unified language how we can query them. It is pretty common. I won't waste more time on that because we started a little bit later than I expected. So I just jump around and expect that most of us understands what SQL is. Okay, so as we mentioned, we have HDFS that contains all our data files. There is one other significant component of Hive, and it is called Metastore. Metastore, I would say that you can imagine that HDFS stores all the data, and Metastore contains the metadata about our storage, about database. So, for example, what kind of tables we have, where we can find those tables in our HDFS file system, what are the columns, what are the partitions, and so on. So Metastore is something that is both part of the Hive and both a standalone service. But actually, it will be important in the Hive architecture. And the other important attribute of Hive is that it is open source. That means every of us can contribute on that, and also everybody who is willing to do that can easily check out the code and check what it exactly does. Okay, I think it will be the next logical step to go there. So what exactly Hive is? Let me talk about that slide. So the Hive architecture, as we mentioned, we have that part, that name node and data nodes. It is actually HDFS. So that is the place when we store the data. And also we have some UI that accesses Hive. That UI can be a single JDBC connection, or Hive provides a CLI-based tool called Beeline, or we can play with that as well. When we execute a statement, like a select statement, it goes to the driver. The driver gets that string, like select one from hello. It has to compile it to something that can be executed to get the data from HDFS. So we have a compiler, it gets the string, and it communicates with the Metastore as well, because Metastore contains the information where is our data exactly. So it creates something that is an execution plan that we call DAG commonly. I won't go to the basics on the execution and the details, because as far as I know, we will have a following up meetup that will be talk about that part in depth. But actually, after we get that execution plan, Hive will execute, we'll ask the execution engine to execute it, and it will be execute, read the HDFS, and Hive will fetch the results at the end. So again, Hive basically is a software that manages our big data. It compiles SQL strings, and you will get your data from tons of petabytes of cluster. I won't go to the execution deeper now because we will have a session about it later. And also there is something important about Hive. It is ACID and it is heavily related to compaction. So I won't talk about it now because even if it's parts of this architecture, the next session with Kokila will be about compaction. So, Hive can actually provide you multiple types of the file formats. The most common are ORC and Parquet, and if you are in a learning phase, it's worth playing with the plain text file. Yeah, and also there is another dimension about Hive tables. They can be external tables or managed tables. The main difference is that actually the managed table is something that Hive completely owns. So it will persist all kind of comments on the table. For external table, the basic example is you can imagine that you want to import a CSV file, a large CSV file, and you can attach it in the external table, and from that you can work on that. And there is one note about the Hive architecture that I want to mention. It is the structure of the table. Basically, firstly, you create one table and you can find, okay, that is too large, so you want to distribute it more smaller chunks. That is the point when you will go and create partitioned table. So it will be partitioned most typically by months. And sometimes you will see, okay, it is still too large, so you can create buckets and on that. Actually, the bucket is computed based on a hash code, and you can imagine that actually it is an algorithm that allows you to separate your data, for example, 10 almost equal size of data. Okay. One important buzzword about Hive is iceberg. It is something that you cannot avoid. All of the big data news are about iceberg. I don't want to talk in deep into that because we will have a following meetup about iceberg. But at the end, there is one important thing that I want to show you. Actually, if you want to get a quick start of Hive, the only thing that you have to do is Google that Docker and Hive. And Hive has its official Docker image that you can pull, and you can execute some basic commands in Hive. That basically means you don't have to install anything except of Docker. When I started to work on Hive, we had to install Java and Hadoop and similar stuff into our computer. But now I would say it is a best way to get started. So again, please try it out. Just Docker pull and try to play with it. Okay, and actually, I think my time is over because we have a couple of minutes to change. So I'm open to any kind of questions. I hope I can answer it. Yeah. And again, I just want to show that slide again. That is the most important part of the architecture. Thank you.
Sorry, I was just wondering, are we trying to asking questions regarding a outdated technology? I'm not talking about Hive.
Yep.
This particular architecture was designed for Hive on MapReduce, which was not even existed in the CDP anymore. So
the reason that is also part of the reason because why I said that I don't want to talk about the execution at all, because to be honest, that is the best picture that I have found in the Hive documentation about the architecture. But since that picture created, the execution changed a lot, and that is why I'm happy that we will have a separated session all about the execution, because it will clear the picture of that. And yeah, I totally agree. That is the reason I would say at our current high-level overview, we can say execution is something just a magic that Hive does with us. And yeah, I totally agree. Currently, Hive uses a way different way to execute. And yeah, thank you for the clarification.
yeah, so I was just wondering. So previously, Hive does not include a execution engine. So so previously, that Hive only having like two major services, which is has a Hive Metastore and the Hive Server 2, right? So the Hive Server 2 is acting as a master services for JDBC connections, and also it's responsible for convert the SQL to a particular execution plan regarding what type of execution engine you're using, right? But later, I think with the Stinger.next project, they invented something called the long live and process, which is the first time that Hive has included a execution engine within the project. So regarding the Hive IRAP versus the execution engine, external execution engine, which is Apache Hive, what would be the major difference on the not on the cache or the daemon, but the executor? So does the original configurations which was targeted for Hive on test, does it also works on Hive on LRAP?
Yeah, unfortunately, I think I'm not the best person to answer that question. I highly recommend you to watch our following meetup about Hive execution, because I'm pretty sure that for that session, we will have an engineer who works directly on the execution part of Hive, and he or she will be able to answer that question with a 100% confidence.
Okay, thank you. And just I think I just got one more question regarding the Hive Server 2. So, so we know that a lot of projects, open source projects, has been leveraging the capabilities of Hive Metastore to be the data catalog of their services, right? Such as like Spark can be attached with the a Hive Metastore to acting as a catalog services. And also Impala doing that as well, although a little bit different. Flink can do that as well, and I believe that a lot of other services are also leveraging the Metastore services as their kind of like unified or catalog services. So that's so Hive Metastore seems to be a successful sub projects that under the Hive projects. And what about the Hive Server 2? I mean, well, it used to be taking SQL queries from the JDBC connections and then converting it to a physical execution plan. So we used to have like Hive on Spark and Hive on MapReduce, and now we have Hive on Test and Hive IOAP. So those are pluggable engines. So I was just wondering, does the Hive Server 2 will be evolving itself into a unified or globally adopted Zscolt front end for all the JDBC connections? So one of the idea that recently emerged, but Hive seems already has that kind of capabilities, what they call the data virtualization. So the basic idea of data virtualization is something related to like data mesh or data fabric. And you have a unified Zscolt front end. You might have multiple data storage or database engines at the back end. But from the virtualization layer, you virtually have access to all the database or data that being managed or mapping to this virtualization layer. So I was just wondering, for the future of Hive, since that the community of Hive does not have much activities for the last 3 years, but the Hive Server 2 is a really good concept for data virtualization. So I was just wondering, is there any plan from the community side that trying to pushing the Hive Server 2 to be a unified data virtualization layer on top of all the pluggable execution engines?
I'm pretty sure that that question it is pretty deep in the architecture of the Hive. To be honest, I would recommend you to ask that question in the Hive development mailing list, because that question should be answered with the PMC members at Apache.
Okay, got it. Thank you.
Yeah, it would affect all the basics of Hive architecture.
Thank you so much, Zol. That was really incredible. The presentation was, and I'm sure many must have get the basic idea about Hive. So I would request Kokila now to move to the next cloud.
Yeah. Hello everyone. I will just share my screen. So as Zsolt has just introduced, and I'll introduce myself. I'm Kokila, working in Cloudera in Hive team. And so currently Zsolt has given you an introduction of Hive and its architecture. So I'll tell about Hive Asset and Compaction and why it is necessary. So as for Hive Asset, transactions and Hive Asset were introduced in 0.13 version of Hive, because if there is a streaming data as such, as Zsolt said, Hive deals with data types, so petabytes of data, and it can introduce so many problems because handling such a huge amount of data requires more processing, and it takes time to run the queries, and it takes time to read the whole files. But then if a query execution runs for long hours, then how do we read it? How the files are stored in HDFS? And it should be concurrent. We cannot just lock and make it exclusive locks, because when we run for long times, it needs to be read by others too. So here is where ACID comes, because we had to support for insert, update, and delete all the statements here. So as such, ACID, as the name suggests, A for atomicity, C consistency, isolation, and durability. So we should have, like, as a transaction, atomicity represents that it should completely complete the transaction, or it should get failed. It should not be any partially successful. And consistency, the data should be completely there, and it should be read once it's completed. And isolation, as such, once a transaction is that's running, it should not interfere with other transaction or application so that it doesn't disturb the other process that's running. And durability, the data should be available and be there for a long time. So here ACID was supported, and this ACID support was only done for the managed tables of Hive, because as for external tables or storage handlers, Hive doesn't have any control over it, and it cannot do any ACID transaction operations on it. And also the key feature for here is that it supports MVCC, which is multiple version concurrency control. Here, there will be multiple versions for the same row, so that the old data, the current data, if a transaction is updating a particular row, the other application which is already reading the data should not get interfered. So for all these things in the storage level layer, MVCC architecture is supported. And as we are using HDFS as the storage layer, HDFS is append only, supports append only file, wherein for each file, when created, it creates a new delta directory. Say we do a transaction insert, and for each insert transaction, a new delta directory is created, and there is a file where the actual data is written. So when there are so many things happening, like in the streaming ingest, while there's a streaming like Apache Kafka we are using, and if there is too many changes and frequent changes happening in the data or the table, there will be delta directories created for each and every transaction that we do. So this creates too many files in this. So here, how the HDFS, here the data file is stored in the ACID transaction. So here, when we create a table, we need this table properties transaction equal to true. Only then this table is considered a transaction table and it supports the ACID properties. And so here, if we do an insert statement to this table, a new delta directory is created in the location of this table. And this delta directory format will be delta, minimum write ID, max write ID, and statement ID. So this write ID is unique in the table level. So for a newly created table, the first insert statement will have 1, and it is incremental further. So minimum write ID is 1. So in this insert transaction, I have a single row getting inserted. So the write ID is 1, maximum write ID is 1, as there is only one insert statement. And this statement ID. This statement ID is if in a particular transaction there are more than multiple statements, this will be incremented. Currently, we have a single one, so it's just 0. And there is bucketing system. We can configure bucketing, number of buckets while creating the table. And since I didn't configure anything here, it's implicitly taken as single bucket. And so we have 0 ID. So the actual data, this 1 and Jerry is written here, ID name. And this is the ACID primary key. This is useful to read the data in the files. So here, this 1 represents the transaction ID, wherein transaction ID is unique in database level. So depending on the number of transactions happening in the whole database, the transaction ID gets incremented. This is the transaction ID, and this is the bucket ID, and this is the current transaction ID, original and correct. So this will be useful while update and delete. So this is for insert, and this is update. So in ACID, update happens with split update concept, which is insert plus update. So when an update statement is done, it will not just update the actual row as HDFS has append only, and it creates a new files. So we have 2 directories created here. One is delta directory and another is delete delta prefix. So delta is used for insert and delete delta is used for deleting. So when we update a row, it gets deleted and a new row is inserted. So previously when we inserted 1 and Cherry, it had the original transaction is 1 and the bucket ID is 0. Now the new transaction ID is 2 because this is the second transaction that we are doing. So in the second transaction, what we have done is update, for which we have to delete. So null. We have deleted the previous data which we have inserted. Now we have to insert the new updated value which we have given in this query. So for this, the new transaction ID is 2. As it's an insert one, this will be original for this. So 2, 0, and 0. And the updated name is written here. So this is how update happens. And if we give a delete query, only this part will be executed. Delete delta file will be created and it will have its original transaction, current transaction. Say we are going to delete now. It will be 1 or 2 because the recent one is 2, and 0, the transaction will be 3. So it will get deleted. So delete happens like this. Now, based on this, there will be delete files for insert, so delta files for insert, and delete delta prefixed files for deletions. Now, if this is happening very frequently in the streaming data, it will be happening continuously, and there will be so many delta and delete delta files that's created. And when we try a select query, or when we read on this table, now the reading should be done to the whole directories, all the directories, delete directories, delta directories, if there is a base file directories. The whole thing, all the files should be read. And in HDFS, to have these files, the metadata also should be kept in the name node. And having so many small files, having the metadata of all the files is memory consuming and also time consuming because we have to read each and every file. To make it efficient for this part is where compaction comes. So as I said, this creates too many delta and delete delta directories in Hive, and this will be too expensive to read as we have to traverse through the whole files. So compaction comes in picture at this point of time, and compaction is done only on the Hive asset tables. So in compaction, there are 2 types, which is minor compaction and major compaction. So minor compaction, as I said previously, there will be many delta and delete delta files like this. So now what minor compaction does is that all the delta files will be combined together and created a new delta file, wherein all this data will be stored here. So if you see here, this is the transaction for 1, first write ID, which will be insert 2 and 3. We have 3 delta files here. All these 3 combined together, this creates a new delta directory, and the bucket ID will be saved. So now, since 1 to 3 data is present, since 1 to 3 data is present here, the new delta directory that we created will have 1 minimum write ID to 3 minimum write ID. So that this tells that from the write ID 1 to 3, all the data is present in this delta file. And if we had multiple buckets, say in this directory, bucket 0 is there, bucket 1, bucket 2, if it's there, then the result would be delta directory, again, bucket 0, bucket 1, bucket 2, because compaction is done per bucket. And again, here, delete delta file is there. So combining all the delete delta files together, it creates a new delete delta directory. So basically, delta files and delete delta files each separately combines together and creates a new directory. This is what minor compaction does. And as for major compaction, so here this combines all the delta files and delete delta files completely together and writes into a single base file. And the base file naming will be the highest write ID. So this 3 is the highest write ID, so it takes the 3 highest write ID. So until 3, all the data will be present here. So in major compaction, as we saw previously, the update, we have one insert. So we have one insert in one delta file, and if we update, we have one more delete and insert for the same row. Now what major compaction does is it removes the older versions of the same row if it is present. So if there is an insert, update, the major compaction takes the latest version of row, say the latest update or delete, whichever. So it takes only the latest and puts into this base file. So all the previously executed transaction for the same row or the particular record, it gets removed. And also, if there are any aborted transaction, say if there is a transaction running and it failed for some reason, network problem or data corruption, anything, it got failed and it is called aborted transaction. And if there is any such transactions, even that gets removed by major compaction. So major compaction takes a bit more time to get completed as it has to do all these things in them. But once it's done, we'll have a single file with all the data. So which makes read easier. Now, how the compaction is done is there are 2 ways to do the compaction. One is manual and the auto compaction. Manual is that we can run the query from the Beeline client or anywhere. We can run the alter table command so that on a particular table, you can either trigger minor or major compaction. And for non-partition table, we can trigger compaction on a table level. If it is a partition table, we can trigger per partition. So compaction happens per partition. And this is the command for that. Alter table name with the compact as the keyword. And I can give either minor or major. As for auto compaction, we to enable the auto compaction, we need these 2 configuration set, but mainly the first one, Hive compactor initiator.on equal to true. This has to be set because initiator is the one that checks whether a particular table or partition is ready to be compacted. To check that, initiator thread has to be up, and in order for initiator thread to run, this particular configuration need to be enabled. And for cleaner, say, cleaner comes down. I'll explain what is cleaner, but cleaner cleans up the data once the compaction is done. These 2 needs to be enabled for compaction to be completely done. So as for the actual compaction process, initiator is for auto compaction, and these 2 comes for manual and auto compaction. So here in compaction, there are 3 threads: initiator, worker, and cleaner. The high level thing that is that initiator checks whether a particular table or a compaction is ready for compaction. Just checks if all the conditions are met and if it's fine to compact, are there enough delta files and everything. And worker does the actual work of compaction, the actual process. And cleaner is that once it's combined and we got the new files, the old files will be there. This needs to be cleaned up. That's what cleaner does. So now if we go into that, initiator. So initiator runs in the Hive metastore as a thread, and it is all in the background, running in background, so it won't interfere with any of the transactions or operations or query runnings on the particular table. And yeah, so it decides whether a compaction can be done or not. So an initiator runs every 5 minutes by default. And we can change that duration in this configuration, Hive compactor check interval. This is in seconds, and by default, it's 5 minutes. So what initiator checks is that it checks whether for a particular table, there is already compactions that are triggered, or it's still working. Because even if we have already triggered the compaction for a particular table, there are still transactions running on tables. So if it's already compacted recently, there is no need to compact it again, or if it's still, the compaction is working. So we skip those tables or partitions. And also, even if auto compaction is enabled, we can specify a particular table to not be compacted. If there is such a use case, it is possible. So for that, all we need is we have to have a table property, no auto compaction equal to true. If we enable this, this particular table will not be considered for compaction. And if we have a table where we are not going to change the data frequently, it's just preloaded and kept, it's used for only reading, then we can use this property. So no need to compact it again and again. Okay. So once these are all done, we have to check whether it's failed compaction too. This is one more condition wherein if there are any previous compactions done on a table, and if those compactions have been failed, and it's been failed consecutively for more than 2 times. Default is 2 times, but we can configure it at any time. So metastore compactor should have failed compact threshold. If this threshold is exceeded, then say if it is 2, and for the last 2 times the same table has failed to compact, then we want to initiate it again. So it needs to be checked and the problem has to be solved, only then it can be compacted again. So the next one is we have to check whether, initiator checks whether minor or major compaction needs to be done on a table or partition. So to check that, these conditions are required. So for major compaction, there are 2 things. One is that either condition satisfies will trigger major compaction. So if there are more than 1,000 aborted transactions for a table or a partition, then major compaction will be triggered, because there will be too many aborted transactions and the data will still be there for which we have to compact it. So we have to remove those aborted transactions. So this will be triggered. And this is, we have so many delta files, and if the delta file size is 10% of the base file size, if there is any base file, we'll compare it with the base file. And if it is 10% of the, exceeds 10% of the size of base file, then major compaction will be triggered. As for minor compaction, we check the number of delta directories. So the value is 10. If there are more than 10 delta directories for a table, then minor compaction is triggered. Also, if there is an aborted transaction which is 12 hours old, it has been 12 hours since the aborted transaction has happened, for that too will trigger minor compaction. And if any table that fits into this condition, and if minor or major is decided, then initiator gets this table and all this information and puts into queue, which is called compaction queue, and with a state I, initiator, so that it says this particular table or partition needs to be compacted with this major or minor, depending on the condition, and its initiator. So we, in the compaction queue, we can check and it will be there, the entries will be there. That needs to be compacted. And this is what initiator does. As for worker, worker is where the actual compaction occurs. And Hive, worker can be run in 2 places. One is Hive server or Hive Metastore. But it's recommended in HS2 because compaction pooling is not supported in Metastore. And we can also configure the worker threads, number of worker threads. If there are more number of worker threads and the compaction runs concurrently, it is faster, but then it depends on the cluster load, how huge the cluster is. Depending on that, the number of worker threads can be configured. And there are two types of compaction. There is MR compaction and query-based compaction. MR compaction is that the merging the file delta files on all the delta files combining together will be done using a MapReduce job. And it just the worker submits that job to the cluster to run the MapReduce and will just wait to finish it. And it will be handled. And there is query-based compaction. And here, everything is run in a queries. So it doesn't matter if there is any kind of execution engine we have which doesn't support MR or anything. Doesn't matter. This will just use HiveQL, Hive queries. And this is mainly used when in cloud, when there is no execution engine for MR. And this, the queries does is that it has 3 stages. One is it creates the temporary table, the same as the original table, and it loads all the ACID related metadata and the actual data into it, creates a temporary delta files, delete delta files, and then also has, after the compaction, it creates a temporary result for it. And once it's done, the original table is mapped to that so that the compacted directories will be read by the original table further. So all these will be in query format. So this is for worker. And once worker completes the compaction, we have compaction queue in initiated state. So what worker does is it checks the compaction queue, takes the record whichever needs to be compacted, and it puts in from initiated state to working state. Once it's completed, it will give it to ready for cleaning state, which means compaction is completed. We can clean the directories which are not, all the delta directories which are not useful anymore. It can be cleaned up. So it will be in ready for cleaning state. Now, what cleaner does is it takes all the absolute delta files which are not used anymore, which are already compacted, and the new directories we have. So cleaner takes all these things and it deletes all the files, it removes. And again, if you still want to retain the directories for some time, or if there is need to be a history of that need to be stored, there are configurations to retain them for some time. So those can be enabled. And once the cleaner completes it, it changes the state to succeeded S, and its compaction is done. So this is what, and these are the cleanup. We can also delay the cleanup with this Hive compactor delete cleanup enabled. And in the interval, the cleaner has to be run. So the configurations are available further. So you can experiment with this if you like. And this is an example for a manual compaction. So just created a table with transactional true and inserted 4 rows, and each insert is a separate transaction. So if you see this table here, we have 4 delta directories created for each transaction. 1, 2, 3, 4. So if we had given in a single insert statement multiple values, then we would have had only 1 delta file because it's happening in a single transaction. So updating, this will be the 5th transaction that's happening, updating here. So for update, there will be 2 things. One is insert and delete. So this will be delete delta 5 transaction, wherein deletion is happening, and an insert, this new updated value will be inserted in the last one, 551. And this delete from student, the delete statement is the delete delta 6. Only delete is happening, nothing else. So this new delta, the actor is created. Now, if we execute major compaction on this manually, alter table compact with major. So once it's completed, we can check, or while working, we can check from the compaction queue table or show compactions. So when check that, if this is in working state, it will show it is in working state. And now since it's completed, we have in completed compactions table where it shows state is yes, type is A, which is major, and highest write ID is 6 because the delete transaction was 6. That's the highest write ID. So it is stored here. And the same write ID used as this is major, a base file will be created for the whole delta files. So here, if you see base 6, this is the highest write ID. So all the data is present now in a single base file. So reading will be much easier when it is of huge data. And the compaction while running, or the running compactions, failed compactions, anything monitoring is there. So we can use these things, show compactions. This will show all the compactions that are completed, ready for cleaning, initiated. All compaction information will be here. Compaction queue, initiated and working, completed compaction. Once it's completed, compactions will have everything. And there is JMX metrics also there. We can check the metrics and monitorings here. That's done. Thank you.
Thanks a lot, Kokila. Anyone has any question? Okay, thank you, everyone. And this session has got recorded and will be published shortly at Insight page of meetup. Thank you, everyone.